待たせいたしました。これよりメドピアトラックでは、Creator of Oxc、ボシェンチェン様によるセッション Oxc The JavaScript Oxidation Compiler をお届けいたします。本セッションでは AI 英語教材 ABC を開発、個人の可能性を最大化する株式会社グロービー様の提供により、英語から日本語へ同時通訳をご利用いただけます。ご希望の方はお席に置いてある受信機をお使いください。なお、受信機はセッションが終了したら本トラックの外には持ち出さず、電源をお切りいただき、そのままお席に置いてくださるようお願いいたします。また、Vue Fes Japan 2024では4つのトラックを同時進行しています。このメドピアトラックについては、画面上の方にありますハッシュタグ Vue Fes メドピアでどんどん感想を共有してください。Mr. Chen, are you ready?それでは皆様、どうぞ温かい拍手でお迎えください。
Thank you. So today I'm going to talk about the JavaScript Oxidation compiler and a deep dive into Oxc, Rust, and performance. To start things off, my name is Boshen, and for the last decade, my job has been a front-end configuration engineer. I configured lots of JavaScript tools such as Grunt, Go, and Webpack. This Grunt is a really old project, same as Scope. So as part of my interest with new programming languages, I started working on JavaScript tools written in Rust, such as Rolldown, ISPack, Biome, SWC, NetPIS. And I used to work on super large monorepos and web apps. For example, I used to work at ByteDance on the ISPack project. And I initiated and led the Oxc project. And now I'm also the member of the Rolldown project, and as well as a member of Voice0 Inc. So what is Oxc? It is a compiler, and it's also a place where you can learn Rust and JavaScript by contributing to the GitHub repo. So JavaScript Oxidation compiler, you can visit at oxc.rs. It is a collection of JavaScript tools written in Rust. Some parts are standalone, and some parts support other projects. The completed tools are the first three: a parser that is 3 times faster than SWC, a linter that is 50 to 100 times faster than ESLint, and a module resolution tool called Resolver, which is 28 times faster than Webpack's enhanced resolve. And the things we are currently working on is called a transformer that is Babel compatible, and it also has a feature called isolated decorations DTS emit. So it's this one. And in the future, we are going to work on the formatter, the minifier, and we also support projects for Rolldown, which is going to be designed for Vite. And also there's a JavaScript runtime called Nova, and it's a pretty interesting project. You can check it out. So at present, a lot of the who's using Oxc, or a lot of the compiler-related projects such as Rolldown uses the Oxc crate. So it's a Rust package for parsing and transformation. The Nova engine uses it for the parsing as well. Rolldown, Biome, SWC node uses the Resolver crate for module resolution. And projects and companies like Preact, Shopify, ByteDance, and Shopee uses Oxlint for linting. So how did it all get started? Oxc started as a learning project for myself to learn Rust, how to write a parser, and also learn about performance engineering. And I wrote a JavaScript and TypeScript parser from scratch, and then the linter as an experiment. And eventually, I just kept going and just coded and coded. So what is performance engineering? The first thing I did to understand what performance engineering is, I went to watch the MIT OpenCourseware, and there's a class called Performance Engineering of Software Systems. And on the first few slides, this is a really difficult concept where he asked, what software properties are more important than performance? So in software, you can you probably want correctness, debuggability, testability, usability, so you have a lot of functionalities. And we often neglect performance. So if programmers are willing to sacrifice performance for these properties, why study performance? And the conclusion is performance is the concurrency of computing. You can often buy needed properties with performance. So what it translates to is performance is used as a budget for buying more features. And eventually, for Oxc, we decided that all performance issues are considered as bugs in this project. So for normal projects, you will think performance is the last thing to think about. But in Oxc, we treat it as a bug if it's slow. And the next concept we learn about performance engineering is called data-oriented design. So I watched this video with the author of Zig, programming language, Andrew Kelly. So Andrew Kelly talked about data-oriented design in his video. And he said when he was young, he didn't understand what, all he did was like OOP and procedural programming. Then he watched some talks about performance. And eventually, at the age of 32, he read the data-oriented design book and finally understand what it is. I too am around 32 years old and read the book and understood what data-oriented design is. And what it means is about CPU architectures and memories on your computer. So it's physically how the CPU is architected on your computer. So in a motherboard, you have CPU cores, and then under that you have layers of cache. So there's a L1D data cache, and then there's a L1I instruction cache. And then you have L2 cache and L3 cache. Then you have main memory. So that's the RAM stick. And so what happens is not all CPU operations are created equal. So on the scale of 10 times, 100 times, and 1,000 times, math operations happen like really, really fast in a CPU. And then accessing the L1, and so accessing the L1, L2 caches, let's say it's 10 times. Then when you go to L3 and main memory, so for these ones, it's 10 times slower. And then when you try to code memory allocation, so these are called system calls, so like kernel calls, it's 1,000 times slower. So in a typical program, what you end up is, so in a computer, CPU is really, really fast. It's like 1,000 times faster than the memory. And memory is order of magnitude slower. So what you want is do more in CPU and do less in memory. And the data-oriented design strategy is find the most used data, make it smaller. I'll say it again. So you, in a program, find the most used data, and then you try to make it smaller in memory and try to do less memory allocations. So this comes to the Rust programming language. So it has lots of unique features, such as memory safety, no garbage collector. There's a thing called, very difficult thing called borrow checker, and there's a Node.js NAPI integration. And for this talk, I'm going to focus on controlled memory management, and CPU instructions in the Rust programming language is optimized with LLVM. So the whole compiler pipeline, it goes from Rust language to an intermediate representation to LLVM. Then you have a CPU instruction that you actually execute on your computer. So for JavaScript, it's really, really hard to optimize, to make it fast. So it's much harder to find data that are more frequently used. For one example, in the TypeScript compiler, so there's a pull request. It has really weird stuff that's called monomorphic no type signature. What it means is in JavaScript, if you make all object for a type with the same shape, So no dynamic access. So all your access is equal. Then the runtime engine will optimize for memory usage, and they made a total performance improvement by 6%. But this PR has been going for a year, and it hasn't been merged because making sure everything is correct is really hard. So for the rest of the talk, I'll talk about performance and Oxc's architecture. So in parser, ASD, linter, transformer, minifier, and the boundary, and give you guys a feel of what it looks like as a performance engineer in Oxc. So the first thing about Oxc is parser, which is 3 to 5 times faster than SWC. It's 20 to 50 times faster than Babel. And it passed all parser tests from test 262 and most of the Babel and TypeScript tests. Okay, this is the first Rust code you are seeing today. So it looks like TypeScript. So there's a pub enum token kind. So what this is trying to say is in a compiler, so if you've written a tokenizer or lexer, the most allocated object is called a token. So in a token, you can store things like a number and a string. And in Rust, you declare as pub enum token kind, and you wrap these two numbers, and you will sum up the total number of bytes. So here it has 8 bytes for the float number and 24 bytes for the string. So if in a program you have 1,000 tokens, you will allocate 24 kilobytes. What you are trying to do in data-oriented design and performance engineering is you identify there's a large memory issue here, and you try to reduce it. So what we did in Oxc is remove these two data to another storage, and then you end up with 1 byte of this token kind. So 1,000 tokens will just be a 1 kilobyte, which makes this whole thing 24 times smaller. So this will make the program faster. And in the token, there's also a start position and end position. So in JavaScript, all you do is it's a number. But in Rust, you can say it's a unsigned 64 number. And there will be 8 bytes each. So that will be 16 bytes. And in a typical JavaScript program, if you declare the position, the start and end position in the source text, it will be a huge file. This is not reasonable. So you can reduce these use64 to use32. So you reduce half the memory usage. That'll be a 4.2 gigabyte file, which is almost all the program you can write. Like, it's still a big program. So with this reduction, you end up with 8 bytes, and you reduce your memory usage by 0.5%. And this optimization improved the performance of Oxc by 10%. And the next thing is strings in normal programs. So in Rust or in JavaScript, you will do heap allocation, which is really slow. And a string has 24 bytes. So it has a pointer, a length, and a capacity. And what you want to do is remove this heap allocation for the program. What you can do is use stack memory, and you try to inline the strings that are smaller than 24 bytes into the string. So this is not doable in JavaScript, but it's doable in Rust. And I used a package for this optimization. So with this optimization, all strings less than 24 bytes will not have heap allocations. And in the parser, there are more advanced features we use from the CPU. For example, there's a CPU feature called SIMD. It's called single instruction, multiple data. What you do is, instead of doing 1 byte at a time, process data 1 byte at a time, you can process in 8, 16, or 24 bytes at a time. And for JavaScript, it's only available in WebAssembly. You can't do it in normal JavaScript. And for example, in Oxc, for finding the multi-line comment, so a comment like this, you have one CPU instruction that process 8 bytes, so that should be comment, COMM, and 1 instruction for the end range. So in a normal program, you will have, say for this thing, 16 CPU instructions, where you end up with SIMD is just 2 CPU instructions. The last concept in the parser, which is for Oxc, which is different from all the other Rust parsers, is called a memory arena. So you may be familiar with, if you're into game design, you normally put objects into one data pool or continuous memory. So in Oxc, when you allocate millions of ASC nodes, they are randomly allocated on the heap. So Rust does not have a garbage collection, so it will just be in random places in your memory, and that's really slow. And when you release the memory in Rust, they have to be released individually, which is also slow. So your solution is allocate a continuous memory region, and then you release them together. So you allocate like a whole memory region, put ASC nodes in it, and then you just throw it away altogether. This will make the program fast. And Oxc uses another library for this procedure. And this also makes visiting the ASC faster because of CPU cache lines. And this change made Oxc 20% faster than its previous version. Okay. Now it comes to Oxlint. You can already try in your project with just one command, npx oxlint, and you will lint your whole project without any configuration. And it's designed to catch erroneous or useless code without requiring any configurations by default. It is compatible with ESLint, and it's 50 to 100 times faster than ESLint with the total number of CPU cores you use. And it now has 432 rules. And this is the benchmark against ESLint. So ESLint takes like 25 seconds. Oxlint is only, in the VS Code repo, it's only 2 seconds. So it's really, really fast. And while I work at ByteDance, the TikTok repo at that time had 122K files. And Oxlint finished in 3.4 seconds. Yeah, that's really, really, really fast. So one of the key features with making it fast is parallelization. So you run on multiple cores, and that's not doable in JavaScript unless you use workers, but workers are slow, and it's not native to the CPU machine. And in Rust, there's just one line of code. So if you have a list of data, you just do parallel iteration, and that's it. And this is a profile of the program, the linter program. So each CPU, so these are 13 CPUs, each one of them is coding code. So to make a program fast, you can profile it and see if all your CPUs are running code. And for the transformer, we can transform TypeScript to JSX. And there's an isolated declaration. So TSC isolated declarations emits. And for its performance, it's 4 times faster than SWC, 40 times faster than Babel. And Babel and SWC uses multiple AST passes. So in a normal compiler design, for one AST, you just run it once, twice, 3 times to get your result. And in Oxc, we try to do single ASD pass. And we also have a minifier prototype. For a minifier, there's a white space remover. So it has 3 features in a minifier: a symbol mangler and a compressor. We aim to have the best compression size. And it's going to be similar to Google Closure compiler. And there will be lots of ASD passes running a loop. And it's written, also, Google Closure compiler is written in Java. It's really, really slow. Nobody can use it except Google. Yeah, and it's slow because you run like hundreds of ASD loops. And it's not possible for us to use it. The only next best thing is Tensor, which is in JavaScript. So we try to improve it by using Rust, mimicking Google Clojure's compiler. And when I talk about performance and trading trade-offs, this is the only time we trade off performance with compression size. So sometimes you go for performance to the extreme, but there are times where you just want to trade off performance for other features. So this time is compression size. And this is a minification benchmark. Shout out to private number. I don't know where he is. He set up this benchmark where he compares all the minifiers. I selected SWC, Tersa, ESBuild, and Oxc minify. At present, it's fastest, 197 milliseconds, but it's also compressed the worst. But you will improve. I hope I can achieve better than SWC by next year. So for Oxc, we not only focus on performance, but we also focus on correctness and reliability. And for a compiler, this is really important because everybody's code, all JavaScript code will run through the compiler, will run through Oxc. So in Oxc, we have a conformance suite on 3 parsers, or 3 test suites, test262, Babel, and TypeScript. So all their test code, we run all their test code as well. And there's a lot of fuzzing. Fuzzing is a technique where you send random bytes, random characters to the program and hope it does not crash. And we have snapshots. We have an ecosystem CI where we run other projects like Prex linter as well. And there's item potency testing. That's where you run a test twice and see the end result is the same. And we also have code coverage. And there's a end-to-end test suite where I selected 3,000 top NPM packages from that I'm going to talk about later. So you can read about our test infrastructure on our website as well. So now to Rolldown. So Rolldown is going to serve as the future JavaScript bundler for Vite. And it has a Rust core, but we are also going to allow JavaScript plugins. And we are going to remove the dev-pro inconsistent issue. So rollup and ESBuild, we remove them and replace it with a single unified compiler pass. And we try to align with rollup's API as much as possible. And since it's going to be fast, the bundler will have more features in the future where other bundlers will not be able to implement. So for Rolldown's performance, I set up a GitHub repo called Monitor Oxc. It uses 3,000 most popular NPM packages from NPM High Impact. So there's a repo where you can get packages with download count of 1 million per week or 500 or more. That's dependent on 500 or more other packages. So a quick Rolldown demo. If you import all 3,000 packages statically into a single file, so one file, 3,000 imports, Rolldown will produce a single chunk with lots of code. It will process 46K files and will generate 809 files with a 200 megabyte entry file. And that's all done in 3.2 seconds. And it only uses 7 gigabytes of maximum memory. So you don't have to use max old space size 8 gigabytes in your Node.js program, which I think most of your big code bases will use that flag. And a lot of projects will run out of memory with Node.js as well. But for Rolldown, we hope that's not the issue anymore. A quick demo. So if you run Rolldown, takes 3 seconds, produces all the files. It's pretty amazing to see it can process so much file, so much code in just a few seconds. So now it's the question where should I run Rust? So here's my answer. Yes, if you like performance engineering, if you want to make things fast and you hate to wait. If you need the strictness offered by Rust, and if your infrastructure has a scaling problem, and if your tooling does not work with so much code, and from personally, if you want to torture yourself, you want to learn Rust as well. Because it's really, really hard to learn Rust. But when you get through the hurdle, it'll be easier. And if there's a Node.js component that can be sped up by Rust, you should also try that as well. So for me, Rust for tooling is already here. You should embrace it. Use Rust and program some small programs and replace parts of your program in your Node.js app to make it fast. And we expect most tooling infrastructure written in Rust by the end of next year. And JavaScript for web development will stay. Vue will stay. Vite will stay because JavaScript still offers you your to make your development faster. And the plugin problem in Rust is still here. We can't do good plugin support in Rust. But plugin support in JavaScript is the thing you want to use at the end of the day. So to learn more, you can visit oxc.rs and rolldown.rs. And we appreciate any kind of contribution. And come to talk to me if you're interested in the project, and I'll show you how to contribute. And that's it. Thank you.